Welcome back. Today's lecture continues where we left off, beginning to explore the ARM assembly language. Today we'll be talking about control flow, arrays, and structs. To start off translating from C to assembly, we're going to produce an intermediate form of C that's a bit closer to the structure of the assembly output we want to end up with. We'll call this Flattened C. In the first assembly lecture, I noted that while loops were an example of a C program component that does a lot of separate small steps. The conditional check, the jump over the body if it fails, the jump back to the conditional check at the end of the body. This is where translating to assembly gets tricky, as statements that don't flow from one to another consecutively are a challenge when each of our assembly statements is one small piece. So recall early in the term we mentioned how goto is awful and we should never use it, except for one particular purpose. Well, welcome to its particular purpose. That's the bad news. Flattened C uses labels and the horrible goto statement from C. The benefit of this, though, is that it's easy to translate into assembly language. You can translate each line of Flattened C to a paragraph of assembly language instructions that is independent of any other paragraph. And using Flattened C then turns one large translation job into a bunch of small independent translation jobs. Our general approach is going to be to invert the condition and jump to the end of the block. We can see this with an if statement. Instead of if some expression, we negate it. We have if not that expression. And then after inverting the condition, we'll jump over the consequent. In our original if statement, if that expression was true, we wanted to do the consequent. Here, the expression we've negated, so if the conditional is true, we don't want to do the consequent, so we're going to skip over it. If there's an else clause, we have all of that same structure, a negated expression, a negated comparison, and jumping over the consequent. But also we need to have in the consequent a jump over the alternative, because otherwise, when we finish off statement N, we would just proceed straight to statement Tn. We would proceed straight to statement F1. And that wouldn't work. We would be doing both the consequent and the alternative. So here we want to have a goto at the end of our if statement, the end of the consequent in the if statement. That will jump out of the if statement to the next line after it in the original C program. So if statements are converted by inverting the condition and jumping to the end of the block. For loops, we're going to do something similar. We again invert the condition and jump to the end of the block, but we also have to remember that at the bottom of the loop body, we have to jump back up to the condition. And in a for loop, which has 3 steps, we have to put the update step at the end of the body, basically converting a for loop into a while loop. Additionally, in a for loop with the 3 steps, we need to have our loop initialization step before the loop itself. That way, it gets done once and never again. In general, when translating from C to assembly, we want to first translate from C to Flattened C, and then build and run the Flattened C code. Make sure it's correct. This is a form of regression testing. It makes sure that in our update, in this case our update of structure of C program, we haven't injected any bugs into the program. If we have a working C program, we can use all of the same tests that we did to assure that it was working, to assure our Flattened C is working, or at least does the same thing. If there was a bug in the original C program, a faithful translation to Flattened C will retain that bug, but it should not inject any new bugs. Once we have this Flattened C, we can then translate from Flattened C to assembly. We build and run the assembly code, making sure it's correct. Again, an extreme form of regression testing. Using that approach, if there are any errors in the assembly language code, they won't be logic errors. They must be simple translation errors. If we started with a working C program, we translated it to a working Flattened C program, and now we have a bug in our assembly, we know it's a translation error. With that new tool in our toolbox, let's drop down a level into the assembly language. Here's our first C snippet. Remember what we saw before and take a moment to think about what it would be in Flattened C. Or better yet, pause the video and write it down. Just like with the in-class iClicker questions, I noted that research shows that students are more likely to learn if you make them actually take a stand, make a decision, commit to it, because if they're wrong, it's harder to just go, yeah, I knew that, and move on, if they didn't explicitly vote or write down a solution. So, take your stand, write your Flattened C. Alright, here it is. We invert the condition and we jump to the end of the block. So if I less than 0 becomes if I greater than or equal to 0, and we jump over the negation. Now let's look at it in assembly. In the assembly code, there's a .section directive to announce the BSS section, and then a .skip4 to provide sufficient space to store an int. This is our variable I. Later on in the program, when we get to our if statement, we have to get i's address into a register. It needs to be an X name of a register because addresses are 8 bytes. So we'll use that register X0 now that we've loaded in the address of I as a pointer. We follow the arrow and arrive at the location of I, and then load the value into W1, a W register because there's only 4 bytes allocated at that location. Now we have to do our conditional. We use the CMP instruction to compare the value in W1 with 0. This sets the flags in the p-state register. Now we want to branch if the result of the comparison was greater than or equal. Note this means the ordering of the arguments to compare matches the flattened C code, not the original C comparison. If the result was not greater than or equal to, that means that I was less than 0, so we need to do the consequent of the original C if statement. We do it. Unary negate the contents of W1 and store back into W1. That's our green line in the assembly code. Because there's no else clause, execution continues on the very next line after the consequent, so we don't need a branch at the end of the consequent. Now let's get a little bit more involved, an else clause. So again, take a moment to think about what will be the flattened C. Will there be any change to the consequent from what we saw before? How will we represent the alternative? Pause the video here if you want to write down your solution. Okay, for the conditional, we have to invert the conditional and jump over the consequent, same as we had before. For the alternative, we just have to do it and keep going. There's nothing to jump over. After the alternative in our C version was just whatever the next line of the program would be. But there is a change in the consequent. Now that there is an else clause, we have to jump over that. So we have this go to end if 1. That stops after setting smaller to be I, us from falling through to smaller gets j. So let's see it in assembly. We get i's value and j's value using our familiar ADR-LDR combination. We compare I with j, and again, note the semantics of the conditional branch fits the flattened C. If I is greater than or equal to j, that should go to the alternative, so jump there. Inside the consequent, we set smaller to be I. We grab the address of smaller and then dereference the pointer to store from the register I is held into that location. At the end of the consequent, we can't just go to the next line because that's where the alternative is, so we need to jump over the alternative. That's an unconditional branch, so it's just a B. The alternative also grabs the address of smaller into X0 and dereferences it to store W2's contents, that is J, into smaller. Seeing that we did the ADR X0 smaller in both the consequent and the alternative, that's certainly one optimization we could make. We could do the ADR before the CMP. That saves us an instruction in our text section, but it's not actually any faster, or at least I wouldn't expect it to be, because the ADR actually only gets executed once in either path. Let's move on, more complicated still, not just conditionals, but iteration. Here's a simple iterative program to compute n factorial. Pause the video here and write your flattened C. Okay, so just like with the if statement, we're going to invert the conditional and jump over the block. Then we have the body of the loop, and at the end, we need to implement the behavior of the C loop, which goes back to check the conditional again. So we have a label at the top of the loop to go, and we go back up to it from the bottom of the body. Let's see how this comes out in assembly. We have our tried and true friend, the ADR plus LDR combination, to get the value of n. We use a register for fact. We don't need to load its value from memory because we're starting off at 1 right before the loop. So just put 1 in the register. That's our green line. Now we're going to do the comparison, and if it fails, leave the loop. Again, the conditional branch semantics match the CMP ordering in the same order as the flattened C. If we didn't leave the loop, we're going to do a multiplication to accumulate fact in W2, and a subtraction to decrement n in W1. Note that we could write these values out to their locations in memory, but it would be silly. We can keep using these values in the register in our loop, and then store them once it's done. At the end of the loop body, there's an unconditional branch back up to the top of the loop to check the loop sustaining condition again. After our loop, presumably the program will continue to use these variables, perhaps storing W2 into fact. Here's another iterative example, this time a for loop in C doing an exponentiation computer. Compute base to the x power and store it into the variable power. Pause the video here and write some flattened C. We have a 3-part for loop. The initialization step goes before the loop sustaining condition check goes at the top of the loop, and the update step at the bottom of the loop that comes back up to check the condition again after doing the update. So in the last precept before the midterm, you covered some new memory sections. I mentioned one of them last lecture, and the other appeared in the appendix. But it occurs to me that nobody remembers anything from a lesson during midterms week that wasn't going to be assessed in the midterm, and that goes as at least double for this year's situation. So, pop quiz. Variables are in what sections of memory? They're all file scope and process duration, so we know it's not the stack. And there's no dynamic memory management, so we know it's not the heap. So here are our options. None of them is a string literal, so we know it's not RO data. We can throw away C. This question boils down to, what's the difference between initialized and uninitialized values? If we know there is a difference, then we can throw away A and B, and now it becomes which one's initialized and which one's not. BSS gets the not explicitly initialized, and data gets the explicit initialized. So that means that power goes in data, and the rest go in BSS. That's E. All right, so that memory aside, let's see the assembly. First, the variables. As noted, power is in data. It's an int, so a .word directive that allocates 4 bytes, and we put the value 1. The rest are ints. They're in BSS, and each get a .skip directive to say this will be 4 bytes. Their initial value is 0 upon the start of the program. And now the code. We'll load power into W1, base into W2, and exp into W3. Now that that's set up with the blue code, we're going to use W4 for I and initialize it to 0 as the first piece of our for loop. That's the purple line. Now the body of the loop. A multiplication that accumulates the register we're using for power. An addition at the end of the body to do the update step. This is the third piece of our for loop, but right now it just sits in the middle of the body. Again, we've sort of translated this for loop into sort of a while loop. So we're accumulating the register we're using for I and an unconditional branch back to the top of the loop to do the check. Again, we could update the values of these variables in memory, but recall that memory writes are several orders of magnitude slower than register writes, so why not do it only once in the final version rather than every time through a tight loop? So now you've seen some examples of control flow. Note that in all these examples we were using ints, signed numbers, even when it was sort of silly, like computing a factorial. So let's see what would change for unsigned numbers. As mentioned in the first assembly language lecture, our values stored in assembly might represent either signed or unsigned numbers. For most arithmetic operations, it doesn't matter, because the bitwise algorithm will be the same. Thanks, 2's complement. But it does matter for division, and to the theme of this lecture, it matters for comparison. Think for a moment about the question at the bottom of the slide. If these are signed ints, the first value is -1, and the second value is 0. If these are unsigned ints, the second value is still 0, and the first value is large, 2 to the 32 minus 1. So that's a bit over 4.25 billion. -1 is less than 0, but 0 is definitely less than 4 billion. So if we're using the same comparison instruction, we're going to have a bad time. We need different branch instructions in that case. We do, in fact, only have one comparison instruction, so we do, in fact, need different control flow or branch instructions. Here are our old ones. And here are the unsigned ones. Unconditional branches don't look at any flags, so they don't need to change. And equal or not equal just check the flag that set whether all the bits were the same or not, so they don't need to change. But for numerical comparison, we have lower instead of less and higher instead of greater. It's a sort of curious naming, changing equal to the same, but that's necessary because of using L for both lower and less. There might have been a better choice here, but I think lower and higher are at least a nice visual representation of what's going on. Just like in the first half of the semester when I guaranteed that you'll get bitten by a switch statement fall-through bug, I almost guarantee that you'll get bitten by a using signed conditional branches when you mean unsigned bug, particularly in A4. I'm tempted to pin a post on the top of Piazza with a running counter that you can increment when it happens to you. In hopes to minimize that rhetorical counter, though, let's change the most egregious of the examples. Recall our factorial program. Let's change the flattened C in only one way, to have unsigned ints instead of signed ints. The only thing that had to change for our unsigned assembly from the old version is the conditional branch. Our multiplication looks the same, our subtraction looks the same, our comparison is in fact the same, but instead of doing branch less than or equal to, we do branch lower or same. There are two other fun control flow instructions to note, CBZ and CBNZ. If you like the opcode C from Toy that took a register and branched if and only if it was 0, these are your equivalents. They're not necessarily used all that often, but if you have a check for 0, it could be convenient to do 2 steps in one. Everything we've seen thus far has just been simple data, ints or longs. Let's see how we'd work with one of our other favorite C constructs, arrays. Here's a snapshot of some array code that has an array of 100 ints. Our registers only store 8 bytes, so clearly we can't read in the entire array into a register at once. Instead, we're going to need to figure out the address of A of I to select it. Recall that for arrays in C, the data is contiguous, and the 0th element is at a lower address than the kth element. Also recall that A of I is really the same thing as the dereference of A plus I, and further recall that A plus I has this implicit multiplication by the size of the elements of A. Whew, that was a whole lot of recall in a row. Feel free to back up, pause, make sure that all of that works for you. So let's look at the BSS section. The array has no initial values, so it's in the BSS. It's 100 ints, so that's 400 bytes. I is a long, so it's 8 bytes, and n is an int, so 4 bytes. Now let's go to the array code. The diagram shows some of the registers, a fragment of the BSS section of memory, with pretend addresses. These are inexplicably in decimal, but hey, despite our drilling, that's probably easier for most of us to count in, so let's go with it. In the C code, we set I to be 2, so let's get that out of the way right now. We'll use x1 for I and move 2 into it. Now, if we're going to do the dereference of quantity A plus I, we'll need the value of A, the implicit pointer to the start of the array. We can do that with our trusty ADR pseudo instruction, just like we've been doing to get the addresses of something in data or BSS that's just an int or a long. Our exact register choice is arbitrary. We'll talk about the rules for register use later on, but for now, let's stick with the first few registers. So we'll use x0, and it becomes 1000. Now the first curious operation. Shift x1 left by 2 bits. Why 2 bits? Is it because we want the index 2? No. The index 2 is the reason we moved 2 into x1 a couple of instructions ago. Shifting left by 2 bits multiplies by 4. 4 is the number of bytes in an int. So this is that implicit multiplication in our dereference of A plus I. x1 is now the ith element's byte offset from the start of the array. Set in C, this says that A of I is 8 bytes beyond the 0th byte of the array. If x1 is now the byte offset and x0 has the base address, we can just add them together to get the address of the ith element. Recall that in the original C code it had n being assigned the value A of I, so we continue to become familiar with this ADR and STR idiom. We have no need for an array index anymore, array address anymore, so we'll reuse the register x0. We store the result we pulled out of the array into another variable, and perhaps you've noticed that these slides were called the brute force approach. This is because we calculated our array address by hand in multiple separate instructions. This worked, but ARM provides us with a more compact and likely faster way to do this, but at the expense of a bit more complicated code to read. So let's go look. Instead of doing a left shift operation and an add operation as separate instructions, we can actually pack these two operations into the pointer dereference using register offset addressing mode. Look at the load in the rightmost box. We have LDR W2, so that's the same. We're loading into W2. But instead of loading from a W0 that was the result of 3 steps, an ADR, an LSL, and an add, we have x0 and 2 other arguments, x1 and LSL2. Those actually look familiar. This is an assembly language shortcut for add the contents of x0 to the result of shifting the contents of x1 left by 2. So we've pulled the add and the LSL into our load. The other advantage, besides compactness, is that the register offset doesn't in fact change either x1 or x0, unlike the brute force one. This is particularly nice if you want to use the base address or the index over and over again later in your program. This was just one of a number of different addressing modes. The only one we've seen thus far, just follow the pointer, is in fact itself a shortcut for an offset. When we want to offset by 0 bytes, we don't have to provide that offset. So the second line here is what we've seen. We can do an arbitrary offset under some reasonable range. That's the first line here. The third version gives a little bit more flexibility as it takes the offset in a register rather than as an immediate value. Note that we don't have that range restriction here. We'll see why when we talk about machine language in a couple of weeks. But it comes down to how many bits it takes to store a literal number in the instruction versus just a register name in the instruction. Finally, the last version on this slide is the one we just saw with the arrays. If it's an array of characters, we don't actually need to do LSL because they're 1 byte each. If it's an array of shorts, that's 2 bytes each, so we'll need to shift left by 1 bit. 4 bytes like we saw for an int, shifting left by 2. And when dealing with longs, we would shift by 3 bits to get 8 bytes to jump over. That's the equivalent of multiplying by 2 to the 3, which is 8. All of these addressing modes, even though we only saw them for W registers, are also available for X registers. Finally, today we'll talk about how to manipulate structures in assembly language programs. Consider the C structure S on the left. We can create an instance of struct S called myStruct. Then we can use the dot operator to access its fields for reading or writing. Let's try to brute force our translation into assembly. Well, the structure has 2 ints, so that's 8 bytes. Let's allocate enough space in BSS for that. The C structs are, by the C standard, required to be stored in memory with their fields in order. So that means that I is going to go first at the address of my struct. ADR to find that address, STR to store into it, great. Now for J. What's the address of J? Well, here we say, okay, it's going to be 4 bytes later. How can we get that programmatically in assembly language? Here's our program, our setup. Which of these is the most appropriate for the last store? C is what we used for arrays when we wanted to have some sort of implicit multiplication. Here we could make this work. If we have a register with value 1, we could left shift that by 2 bits to get the value 4, and then that gets added to x0 to get the spot of j. It would work, but it seems like a lot of work for what should be a simpler computation. Maybe there's a better option. We could make B work, but we'd have to add 4 to x0 first to get the spot for j. Maybe there's still a better option yet. D could similarly work if we had 4 in a register, but if D works when the value 4 is in a register, can't we have the offset just be an immediate value? We said that the offsets with immediates were limited by a range, but certainly 4 is within that range. So A works with the immediate value 4 as the offset, and A is really the cleanest solution here that requires no additional setup. Here's our result with A. This works, but be careful. Here's another program. This looks just like the one we just did, except with the character as the first field. Thinking back to what our program looked like, it should be pretty much the same. When we stored into the first field, now we want to do an strb to store a single byte instead of an str to store 4 bytes. And then when we do the register offset at the end, rather than adding 4 as the offset, we'll want to add 1. That should be perfect, right? As you know, when I use that tone of voice, the answer is always no, wrong. When you learned about structs way back in that utterly ridiculously packed precept with command line arguments and all of dynamic memory, it might have been said, or it might not have because of time, that the size of a struct is at least as big as the sum of the field sizes. Because of a choice the architecture can make for performance reasons that it might prefer to have the fields and memory addresses with nice alignment, say a multiple of 2 or 4 or 8 or 16. If the architecture prefers it this way, there might be padding inside the struct. And that's what actually happens here. There's a 3-byte pad in between the character and the int to make sure the int is still aligned at a nice location. The structure itself will be well aligned, so the 0th item typically we don't have to worry about. That means that our actual program, when we see it, we do have that strb to write a single byte instead of writing 4 bytes. But we also have this str still with an offset of 4, not an offset of 1 as we might have guessed. If you're going to compose assembly language that uses structures that were placed in memory by a compiler, then you must know if the compiler added padding. Here are the rules for AArch64 with ARM. Within a struct, fields must begin at the addresses with evenly divisible or aligned in this way. Also note the compiler may add padding after the last field of a struct, and the reason for this is, as I said on the last slide, we think of the compiler or whoever wrote the code, that might be you, as putting the address for a struct's first field at a well-aligned address. But if we have them in an array, we don't necessarily have this guarantee. Because of this, the compiler may add padding after the last field to make sure that inside of an array, the next array element, its first field will be well aligned. With that introduction to Flattened C and branching, you're ready for the first part of assignment 4. Go find a partner, hopefully from your own time zone, and start it now. And with the discussion of arrays, structs, and the fancy addressing modes, you're almost ready for the larger second part of the assignment.